expect. Okay, so I'm going to start off by reminding you what we did last time, which was we started talking about volumes. This is part 2 of section 6.2 on volumes. Yeah? All right. So this formula I gave you all last time. It's how to find a pretty general volume if you can find the area of a cross-section. As long as you can find the area of a cross-section, and specifically a cross-section that is perpendicular to the direction of integration. If you can find it, well, then this formula here will be your volume. And there's a similar formula if, let's say, you find the cross-sectional area perpendicular to the y-axis. So if, let's say, A of y area of a cross-section perpendicular to the y-axis, and the solid extends from, let's say, y equals c to y equals d, then the volume will be the integral from c to d of a of y, now to be a dy integral. Here's a little warm-up question. Suppose that D is the disk of radius 1, which is centered at a certain point in the xy plane. Let's say centered at the point xy equals 3, 0. Now, I want you to do something in your mind and tell me what shape you get. What shape you get when you revolve D about the y-axis? And you can private message me your answer. Oh, that's not disk, sorry. Disk. The disk of radius 1 centered at xy equals 3, 0. So what shape do you get when you revolve it about the y-axis? This is a 3D shape. D itself is a 2D shape, but when you revolve it in 3 dimensions around the y-axis, you should then get a 3D shape, which I'm asking you to describe. What object that you know and love does it resemble? Private message me. See if anyone's getting it. Oh, Serena got it. Stanley got it. Jolene got it. And in order to help you, I'll start drawing it. So, there's 3. All right, so it's a disk of radius 1 centered at 3, 0. What do you get when you revolve this region around the y-axis? Y-axis, as usual, points straight up. It might help to draw its mirror image on the other side of the y-axis, which in this case would be a disk over here. It's often useful in drawing the picture. Juliana?
We're assuming that the disk is perpendicular to the x-axis, correct? Or is it not perpendicular, or is it just like it's in the plane of the x-axis?
Yeah, it's in the XY plane.
Okay, so we're not assuming that it's flat, essentially.
It is flat in the XY plane, and now
Right.
rotated in 3D.
Okay. I thought it was flat, like I thought it was like on the plane of the x-axis for some reason, but that makes sense.
So let's see. A few people, yeah, Giselle got it, Jacqueline got it. So a few people have correctly said what it is. Which is a bagel. If you said donut, you were wrong. I'm sorry, it was a bagel. Just kidding. A donut or bagel are both correct answers. The technical name is a torus. Okay. So you kind of have to do this rotation in your head, and you know it's kind of hard for me to draw, but this image right here is kind of looking at it face on and cut in half. So it's kind of hard to draw the rest of it. Okay, so that was just a little bit of spatial reasoning warm-up. A lot of these problems are about visualizing shapes in your head. Probably the hardest and most interesting part of all the problems that we're going to do today and in this section. So, like I said, I basically got 3 examples today. First one is this one. So we're going to let R be the region bounded by these 3 curves. Let me graph the region R so we have an idea of what we're looking at. Okay, so there's the region R, and we are going to rotate it around the y-axis. Oh, crap. I wrote the question wrong. That should say the y-axis, not the x-axis. And there's actually an animation that I can show you to demonstrate this. So how about I'll show you the animation now. So there's the region R. And when we rotate it around the y-axis, it's like sweeping out that region. That's the region that we want to find the volume of. I thought it looked kind of like a shot glass. And the way that we find its volume is with cross sections. The cross sections look like, well, the word that they use is a washer. It's also called an annulus, and I'll explain that in a second. But right now, when I turn on the approximating washer, that is through the cross section that we need to find the area of. So I'm just going to use this picture here. So our cross sections they are not discs anymore, but it looks like sort of one disc inside another, or rather a disc with a smaller disc removed. There's a special name for that. and it's called an annulus, or a washer. So an annulus, or washer, is a larger circle containing a typically concentric smaller circle. And if the smaller circle has radius, let's say r in for inner, and the larger circle has radius r out for outer, then we can find the volume, or sorry, the area it's pi times, it's the area of the bigger disk minus the area of the smaller disk, which comes out to be pi times the outer radius squared minus the inner radius squared. Okay, so that's going to be useful because the cross sections in the problem at hand are indeed annuli, or washers. Sometimes we refer to the method of solving this problem as the method of washers. And we can find their area as long as we can find what the inner radius is and what the outer radius is. And for that, you have to use some geometry here. So let's sort of zoom in on the shape at hand. And this is the most interesting part of the problem. First, we are integrating in the dy direction. You have to make that decision at the beginning of this problem so that you know how to proceed. Knowing that, we need to get everything in terms of y. So if I pick an arbitrary point on the y-axis, let's just call it y, I need to find, well, the cross-sectional area, which means I need the inner radius. And I'm also going to need the outer radius in a second. But let's focus on the inner radius first. In order to find it, I need to know something about this curve. This curve was given in the question to be where y is equal to x squared. So a point on that curve, which has coordinates x comma y, well, y is equal to x squared. So I can get x equivalently. I could say x is equal to the square root of y. Remember, I'm keeping in the back of my mind that I want to get everything in terms of y. So that's why I'm going to write this point as square root y, comma, y. And then you can see that your inner radius is, well, it's equal to your x value, which we just decided is the square root of y. Okay, that right there is probably the hardest part of the whole problem. I also need to find my outer radius. Oh, we want the coordinates in terms of y because we are integrating dy with respect. That is to say, we are integrating with respect to y because the region is rotated around the y-axis. The technique that we learned means that in that case, for a solid of revolution, you're going to do a dy integral. our outer radius will be the distance from the y-axis to this line, which, if you remember what the problem said, that line is where x is equal to 4. So our outer radius is just constantly equal to 4. It actually never changes. I suppose I will also need to know what our limits of integration are. So I'll need the minimum value. And I'll also need the maximum. Ooh. Anyone know what the maximum y value is? It's not 4. That's the maximum x value.
16.
Oh, yeah, because it lies on the line where y is x squared. So good. Apparently it's 16, and you can see that because it lies over where x is equal to 4. Good. So we now have everything we need to find the volume. So the area, the cross-sectional area is a function of y, which is, since it's an annulus, is the outer radius squared minus the inner radius squared times pi. Will thus be, okay, outer radius is 4. Inner radius, we figured out that that was root y. So now it's just, we can just do the integral to get the answer, although this part's easy. I don't really care about exactly what the answer is. The point is if you can set this integral up. So we saw it went from 0 to 16. And the cross-sectional area is 16 minus y. Cool. So yeah, that's the main thing. And if you want, you can write down what it is. Which is 128 pi. Any questions?
Yeah, I have a question. So would like a good rule of thumb to kind of like figure out which R is like which equation goes with, or to figure out like which is your R inner and R like outer, is that just to look at like how it's defined by like which equation? So we know that like the further part of the graph, which would be like R outer, would be defined by x equals 4. So you know like that's the equation that you need to use to derive what like R out would be. Whereas like the inner equation is y equals x squared. And so that's like, we would use that to define like the inner R, correct? Okay.
Yeah, it depends heavily on the geometry of it.
Right, because I know every graph is different.
Yeah, so I would recommend that you get in the habit of drawing pictures.
Mm-hmm. Yeah.
All right. Cool. So I guess I can do my pyramid problem now. So the next problem we're going to do is to find the volume of the Great Pyramid of Giza, supposing that its height is h and that its base is a square of side length L. And we're going to find its volume. And here's a picture of it, which is kind of cool because in the picture it's painted white, which is apparently how it was constructed back in the day. So, 2,000 years ago, when you would see the pyramid from like 100 miles away in the desert, it was blindingly bright. It reflected the sunlight because they had it painted white. So if you think it's stunning now, and I believe it is, though I haven't seen it myself, it would have been even cooler if you could have seen it back, when it was painted white. We're supposing that the base is length L, side length L, and that the height is h. So height is the distance from the peak to the ground, vertical distance from the peak to the ground. In fact, in order to find its volume, I think it's going to be a little bit easier if I turn it on its side. This is not necessary. So for finding volumes of pyramids, there are many different ways you could do this. I'm just going to show you one way. And in order to do it, like I said, I'm going to turn it on its side like that. And I'm going to put the origin right at the peak. And I'm going to have the x-axis and the y-axis in the usual directions. So it's kind of like that. In fact, I already made a picture, so I don't have to spend too much time drawing a picture for you all. So here's a picture I sketched out of the pyramid on its side with the origin at the peak and opening, as you can see, along the x-axis. So, like this side right here, we already know is of length L. So that means that this side right here is of length L over 2. The height is h. So where's h in this picture? Let's see.
Can we assume that it's the length of that smaller triangle is L over 2 because the origin cuts it in half?
Yeah, by the symmetry of it. It's the distance from the center of a square to.
Oh, okay. That makes sense. Okay.
And so yeah, the height is h. Okay. We ultimately, well, we want to find a cross section, and I'm going to do this by integrating in the x-axis. So my cross sections are going to look like squares. In fact, I think I have a little animation I can even show you of that. Let me show you cross sections real fast. There, so there's a sphere, and as you make slices parallel to the base, you can see the cross sections are squares. So since we're integrating in the x direction, let me choose some point on the x-axis. Let's say a point right here, at some point x. Okay, now let me try to draw a cross section. So there's one of my cross sections, and it's shaded in. Cross sections are squares. Let's suppose that their side length is s. So if I can figure out what the side of the square is, then my cross-sectional area will be s squared. Sorry, no, that should be of x. I just need to get that in terms of x. So that's the challenge. That's where we're going to have to use some geometry. So let's zoom in on this shape. I did a problem like this in office hours yesterday, and I just made up the problem. It turned out to sort of take a while. The method that I used was the method of similar triangles. That's one of the ways to do this problem. The book does an example like this, and I believe they use similar triangles. Yeah, it's example 8 in the textbook. So you should review that and review similar triangles. I'm going to do it a different way, just so that I can expose you to multiple ways of doing it. The way that I'm going to do it is I'm going to find the equation of this line right here, because it's a line through the origin, which means its equation is y equals mx. We just need to find m, right? There's no y-intercept when it passes through the origin. But I can see what its slope is because I can see what its rise is and what its run is. You can read the slope off from the picture right there. So here, let me just calculate m. The slope of that line is the rise over the run. The rise is L over 2. The run is h. So apparently, that line is the line L over 2h times x. Yeah. And in particular, if our x coordinate is x, then the point above that x coordinate on that line is the point xy, where y, as we can see, is L over 2h times x. So that's going to be the point where, again, y is L over 2h times x. Why do I care about that? Because the length, the y value at that point is exactly this little purple segment that I just shaded in, and that is half the length of the square. Juliana?
Yeah, so I had a question on specifically why we chose to find the equation of that blue line. Is that because it coincides with the side of the actual pyramid, and that's where the edge of the cross section is going to touch?
It's because it allows us to find this red segment that I just found.
Okay.
And once we know that distance, then we can double it to get what S is. So this red segment right here is half the length of the side of this square. So now that I know that S is L over 2h times x, I can get the area of the cross section in terms of x. Right? So
Professor, wouldn't it be S equals 2 times ln over 2?
Oh, 2 times that. Thank you. Yes. So I can actually cancel a factor of 2 here. So S is L over h times x. And my cross-sectional area will be L over h times x quantity squared. And my volume, let's see, we extend starting at a minimum value of 0, extending to a maximum value of h. Our volume will be the integral from 0 to h of L over h times x quantity squared dx. And, well, from here on out, it's just automatic. We get L squared over h squared, 1/3 h cubed, or 1/3 of L squared times h. All right, any questions?
Would you say that this is a problem that's like most likely that you guys would give us, since there's no actual, I guess, values given?
Good. Although, you know, I would probably give you the Sphinx, not the Pyramid of Giza. You know the Great Sphinx? No? Here.
Oh, Professor, I have a quick question about your answer. Is that supposed to be an x or an h cubed?
Neither? Here?
Yeah, I guess like, I don't know. I wasn't, oh, never mind. We plugged in values for X. Never mind.
All right. Any other questions? And yeah, Juliana was asking if this is a good test question. I mean, yeah, it is. Like, well, actually, just because I used letters for the dimensions, that's not the hard part. That makes it harder. But even if I had given you numbers for the dimensions, it's still kind of tough setting this up, coming up with the geometry. So whether I use numbers or letters, in either case, this is still a good question, and something you should know how to do. And please check out the example in the book where they do it with similar triangles, because that's also a good method to know. And I just don't have time to cover it right now, although I did do them in office hours last time. So I have one more example today. Oh, I have a cool question about pyramids, which is like, where would you have to slice a pyramid? All right, imagine that at some height you sliced it. Where would you have to slice it to cut the volume in half? Right, at some height, you would have to slice, you could cut the pyramid in half. Obviously, the top piece is, well, in this picture right now, it looks a lot smaller than the bottom piece. But at a certain height, you would have just as much volume on the top as on the bottom. I challenge you to figure that out, although unfortunately, I don't think I have time to do that right now. Maybe at the end of class, if we have time, I can answer that question. Or if this is all super easy for you, then I challenge you to figure that out in the meantime. But I have another example, which is something new, something that we haven't seen yet. So there's a certain type of problem where it's not a pyramid, it's not a cone, it's not a volume of revolution. It's where you have some region in the plane, some base region, and then you predefine what the cross sections are supposed to look like. So the problem just tells you that your cross sections look, for example, like semicircles or triangles or rectangles or squares. So my example will give you the choice as to what our cross sections should look like. I'm going to let you all choose. We are going to start with the base region that's bounded by square root x and x squared. So let me just show you what the base region looks like. There's our base region. And the way these problems work is you are told what your cross section looks like. So for example, if your cross section looked like semicircles, then your shape would look like this. And you kind of have to connect all the tops of the cross sections together. Or if your cross sections look like triangles, maybe in that case, it would all look like this. So why don't you all vote? Which cross section do you want for this problem? Let me bring up a poll because I already created one for the purpose of this. So go ahead, choose the cross sections that you want. And I already know what the last class chose, so it'd be kind of funny if you all choose the same one that they chose. Let me show you. I can also show you an animation of this. So,
For most of these problems, Professor, will the problem like tell us, or will we have to choose?
It'll tell you. It's not going to let you choose. I'm just doing that for fun.
Okay. I was like, that's kind of weird.
Yeah. So there's that region. And like I said, you can either choose squares. And in that case, these would be your cross sections. Or if I drew a whole bunch of them, it would look like that. So that's the shape you would get if your cross sections look like squares. By the way, I specified the cross sections were all perpendicular to the x-axis. Again, that's something that was just specified in the problem. It was given to you that the cross sections are always perpendicular to the x-axis in this problem. If they look like equilateral triangles, then they would look like that. And the actual volume of the shape would look something like that. And if they were circles, semicircles rather, which, oh man, you all, of course, chose the same thing as the last class, which is semicircles. You know, I think there's a great quote about the predictability, like how you can't predict what any person's going to do, but you can be incredibly predictive about what groups of people are going to do. So yeah, humans are not predictable. Groups of humans, highly predictable. So yeah, sure enough, this group of 70 students made the same choice as the last group of 70 students with almost the same percentages too. So that's kind of interesting, which is semicircles. Semicircles look like this. Okay. Looks kind of like half of a fish or something. So let me take a snapshot.
Is the x-axis still the red and the y is still the green?
Correct.
Okay.
So we're doing this problem where the cross sections are semicircles. It might help to know what the volume of, area of a semicircle is. So let's say that this is a semicircle of radius r. In that case, the area will be 1/2 pi r squared. So if we can find what the radius of these semicircles is, then we can find their area. So let's see, remember, there's the x-axis, there's the y-axis. Let's pick some arbitrary point on the x-axis. On the blue line, that blue line is where y is equal to x squared. On the red line, that red line is where y is equal to the square root of x. So above our point x, I can find, say, the coordinate of this point. That's where y is x squared. Okay, and if I go up above it, right there is the point where y is the square root of x. So I can find the distance between those 2 points. And I'm going to call that distance d. And d is going to equal, well, the point on top minus the point on the bottom. The y value on top, rather, minus the y value on the bottom. Someone who hasn't said anything yet. What does d have to do with the semicircle?
Is it twice the radius?
Ah, good. Yes, it's the diameter, which is twice the radius. So yes, that's d. So this is also equal to twice the radius. So the radius is 1/2 of d, which is 1/2 of root x minus x squared. And now I can just plug it into the semicircle formula. And we're good to go. Oh, I guess I'll need my minimum x value. And my maximum x value. So my volume will be from 0 to 1. 1 half times pi times half the radius squared. Cool. Yeah. And there we have it. Whatever that is, I guess I can simplify it a little bit if you all want. It's what, pi over 8, 0 to 1, root x minus x squared dx. Uh, 9 pi over 560, I guess. Or 0.05. Cool. All right. Any questions?
If this wasn't on like a coordinate graph, and we wanted to find like the limits, do we just like set the two equation equals to each other to find the intersection?
Yes. Yeah. That's how like you could find that point up there. Yeah.
Okay, thank you.
Mm-hmm. Yeah. Ended like right on time. Cool. Well, that's all I technically or officially have for lecture today. So good luck on the quiz tomorrow. And I'll see everyone on Friday, and I'll hang out to answer questions.